This is the short summary for Chapter 5. The focus of Chapter 5 was on type classes. In particular, I motivate why type classes are useful and how to implement them, and also how to understand them as functions at type level. The motivation is that we want to write generic functions that are parameterized by some parameter that cannot be any type parameter. It must have some additional property, such as being a numeric or summable or something like that. Similarly, we want to define some function that can be used with arbitrary type constructors only that have a certain method, such as functor method map. In order to define such functions, we need type parameters that are restricted to a certain subset of possible types. And this is similar to partial functions. These are functions whose values of arguments are restricted to a subset of possible values. So let us consider partial functions in some more detail. So functions can be total or partial, and I'll explain how that works. And also functions can be from value, from type, to value, and to type. We can consider all of those possibilities, and I describe what Scala code is for that. Now, partial functions can be also from value to value, or from type to value, or from type to type, and so on. And I give examples what happens when a partial function is applied to something that is outside of its allowed range of values. Then for value level functions we have an exception, but for type level functions we have an error at compile time, which is okay. And so what we would like to do now is to learn how to use partial type to value functions. So I explained that if we knew how to do that, then we would have safe code, which would be compile time safe, where we would, just like we know that partial functions are safe in certain places, because they will actually never give any exception, we would like to have partial type to value functions that are safe in certain places. Here's an example of partial type to type functions. It's a so-called generalized algebraic data type, not a good name. This is really just a type function, which is a function from type to type, and it's only defined for certain arguments. So I explain why that is so and why it cannot be a functor. Another way of defining it is a trait with a method, and the case class is extending the trait and overriding the method. But this way of defining a partial type to value function this time has limitations, and the limitations are that it's not extensible. You cannot add new functions later, and you cannot use this in other partial type to value functions. Everything has to be defined up front. To fix that, we use a trick, which is that we add an extra argument to functions, which is called type evidence. And so then a function that needs to have a type parameter restricted to a certain subset of types receives an extra argument that is the evidence that this type is of the required type. And that is explained in detail in the tutorial, how that works. So these type evidence values are central in the implementation of type classes. We show that this solves all our issues of extensibility, and it has costs, but they can be mitigated using the implicit feature of Scala, which I explain. Implicit arguments are automatically passed to functions as long as they are declared and I show how that helps us define type classes. Now, type class is basically a set of partial type to value functions that share the same type domain. The type domain is declared using a partial type to type function. So the specific code, as I show, needs to have first a partial type to type function and then one or more partial type to value functions. Now, I also emphasize that there are some algebraic laws to be satisfied, but this code does not directly express the laws. I explain the terminology that we use when talking about type classes, such as type belongs to type class, or there's a type class instance. A typical implementation in Scala I show in detail. There are many ways of implementing a type-to-type function, partial type-to-type function, and partial type-to-value function, but they're all typically with implicit values of the partial type defined. So this type evidence value needs to be declared in some place and then used elsewhere. So I show examples in code how additional partial type to value functions with the same partial type to typed function can be added later. So that is our extensibility. As examples, I give semigroup, pointed, and monoid. These are implemented in different ways. We don't need to use traits. There are all kinds of different ways of implementing type classes that can be used in different cases, but they're all always a partial type to type function and the corresponding one or more partial type to value functions. I show that for the functor case, and in particular I show how to implement a generic function that checks the functor laws, and it's parameterized by an arbitrary functor. I also introduced the notion of kind. So kinds are kind of a type system for types, and so kind could be understood as also describing type classes. This is usually not done, but I think this is quite reasonable. That star with a constraint that there must be a type class. And then type constructor has this kind, and it also can have a type constraint, so you could have notation for that. I show how to declare Scala syntax, which is very convenient to use when dealing with type classes. This is specific to Scala, and the result will be that code is shorter. I give a lot of examples of different type to value functions, partial type to value functions, declared in various ways, not necessarily using traits, because this is not essential. Essential is that there is a partial type to type function and a partial type to value function. I also talk about cats library. Cats is a library that has different type classes, such as bifunctor. A contrafunctor is a type class also that can be defined. Cats library calls it differently, it calls it contravariant. And I show how to use type classes to implement the functor construction in code. And there are exercises that are similar to the worked examples just shown. I give some further hints about what can be done. Now I summarize the problems we can solve and the problems we cannot solve, and libraries and tutorials that can help you if you want to go in those directions, such as different recursion schemes and automatically deriving type class instances.